Okay, hello everyone. Let's wrap up this lecture, finishing up our discussion on valence bond theory here. Talking about how simple orbitals combine to form a chemical bond. Okay, so now let's draw the Lewis structure and the valence bond description of the chemical bonds in N2. And let's comment on, some similarities and differences in the two descriptions, okay? All right. So N2, we're N2, we have 2 nitrogen atoms times 5 valence electrons each, and we get 10 electrons, okay? So here we can see we have 2, 4, 6, 8, 10, but we're missing some octets in our nitrogen atom. So let's convert some of these bonds here into maybe a triple bond. Okay, so we're going to write now nitrogen, 2, 3. So we put 2 lone pairs as now bonds between the 2 nitrogen atoms, and we get the nitrogen molecule, the dinitrogen molecule, and that's a pretty good structure here. So we have a triple bond and 2 lone pairs on the nitrogens. Okay, so if we think about the 2 nitrogen atoms, right? Nitrogen is 3s2 and then 3p3. So each nitrogen atom has this electron configuration. Here's the S, here's the 2p, 2s, 2s. So both these nitrogen atoms can combine here, and we can form several bonds between the orbitals. Okay, so let's say this is one nitrogen atom. So here's my first nitrogen. And then next to it, we're going to draw another nitrogen atom. Okay, so it has a set of p orbitals that are going to combine here to form a pi bond. And then on the atomic axis, we're going to draw another set of p orbitals that indicate this is the sigma bond. So we have a sigma bond here. So a bonding interaction. So this will be the sigma bond, and this will be one of the pi bonds. Okay, so that accounts for one pi bond, right? But there should be another pi bond. So let's draw this bond a different color so we can differentiate it. So there's going to be another bond that's going to come out here, and that's going to be the other pi bond. So say we have a pi bond that's sticking out right here. Okay, like that. And let me just clean up a little bit here. Oh wait, sorry. Like that. Okay. And now this bond, we're going to connect to the other triple. So the triple bond is going to be this interaction between the other pi bond, set of pi bonds. So that's a triple bond. Okay. So that will give us our sense of where the bonds are for this molecule. And it looks very similar to what we've drawn up here for oxygen. Okay. Okay, so let's comment on them. So it predicts we should see one sigma bond. So one sigma bond. Then 2 pi bonds. Okay, so that's pretty good. So our model does predict we should have a triple bond, and we could do that in our valence bond model. And then we see here that the the three electrons in each of the p orbitals are going to combine to form one sigma bond, and then two pi bonds will result from there. And then the lone pair in the 2s, we can't actually show that yet. So that's where they kind of differ here. So we can't, so lone pair on nitrogen atom, not shown in the model. Not shown in the model. So it's shown in the Lewis structure, right? But it's not shown in this structure. And we're going to go into why that is, okay? So let's move on here. So that's like a typical question, you know, I like to ask, where I have you draw the structure of the molecule and draw all the bonds involved, sigma and pi bonds. So here's the pi 2 bond, and then here's the pi 1 bond, okay? So we have a pi bond. Oh, wait, I already drew it. We don't need to draw it again. Good. There we go. Okay? All right. Let's move on here. All right, now let's talk about hybrid atomic orbitals. So we kind of touched upon it when we were talking about the different shapes, but now we're going to talk about what it actually means. Okay. So hybrid atomic orbitals. So when we were talking about valence bond theory, so far we consider simple molecules, diatomic molecules, and using valence bond theory, that was easy to predict the bonding. But this approach is not great when applied to more complicated molecules such as CH4 and water. So molecules that have more than two atoms in the structure. So let's go over that. So the electron configuration of carbon has only two unpaired electrons. So by that logic, it should only form two bonds, right? Because it only has two unpaired electrons. But we know from calculations and just from looking at carbon in general, it likes to form four bonds based on Lewis structures for like CO2, methane, carbon dioxide, methanol, etc. So how can we explain this like discrepancy here? We can say, okay, we know that it takes relatively little energy to excite one of the electrons from the 2s orbital into the 2p orbital to give four orbitals that now have only one unpaired electron. So the reason we can promote this electron like this is that because the energy that's put in to promote this electron, it's more than compensated by the amount of energy released when we form two more bonds to carbon. So the bond making process will more than satisfy or compensate the energy invested to move the electron to the p orbital. So that's the basis for hybridization. So that's hybridization in a nutshell. Okay. So if we do this, now we have four unpaired electrons, and now we can form four bonds, and that's usually what happens for carbon. Okay. So now we run into an issue for problems predicting geometry. We have four potential bonds to form, but now the geometry we run into trouble here. So let's consider the water molecule. If we combine a pair of hydrogen atoms with unpaired electrons in the 1s orbital, and then with the two unpaired electrons on an oxygen atom from the 2p orbitals, we get the correct number of bonds, right? We get two bonds, and we should have two lone pairs to form four electron groups around the atom, right? However, we're going to have a flaw here. It predicts that our angle for HOH would be 90 degrees instead of 104 or 105. So this would be approximately 90 degrees in this model, right? But we know from experiment that the bond angle in water is nearly 15 degrees higher, 105. So this can't be this. We run into the issue here. So to solve this problem, we can assume that the valence atomic orbitals on an individual atom can be combined to form hybrid atomic orbitals. Okay, so oxygen can form orbitals by combining it's best if we so it's best to consider that these orbitals, instead of bonding directly to their atomic orbitals, we can make a hybrid of orbitals that give better shapes. Okay, so oxygen is a bad example to go over though, so we're going to use a different example first. So let's consider the beryllium atom in the BeH2 molecule, beryllium hydride. So the geometry of this molecule, we can explain it by promoting one electron to the p orbital. Okay, so one electron from the s orbital gets promoted to the 2p orbital. So now we have two electrons that are unpaired. And then, so the result is we can mix two of these orbitals now to form two sp orbitals. So that's called mixing. And that's what we call hybrid orbitals, because they're a mixture of both s character and p character. But you see now, we only now have two orbitals, and they should be of equal length. And then we should have better bond angles to represent the structure. Okay? So one key part of this is the number of orbitals used to make hybrid orbitals must equal the number of hybrid orbitals produced. So if I use two orbitals, like in this example, I must produce two hybrid orbitals so that mass is conserved, or matter is conserved. Okay? So the picture is like this. So we kind of think of it, we split the molecule in half, and we're going to form a hybrid of 2s plus 2p. So the 2s, the combination is the orientation of the p orbital. So when it's positive, it's facing to the right, and when it's negative, it's facing to the left. So we get the formation of these orbitals using this mathematical construct. Okay, so we can apply this to other molecules such as BF3 with 3 domains. We combine 3 orbitals instead of 2. So we promote one s orbital to the p orbital to get 3 equivalent sp2 orbitals for boron. And then for 4 domains, we can combine the s orbital and 3 of the p orbitals, promote the electron to the empty p orbital, and then we get 4 equivalent sp3 orbitals in this one. And then with 5 domains, we promote an electron not to another p orbital, but to a d orbital, so we can get 5 sp3 d type orbitals. And for 6 domains, like for neon, for sulfur, we promote 2 electrons from the s and the p orbital to the d orbitals, to the d orbital. And then we combine 6 orbitals, and we get 6 sp3 d2 type or hybrid orbitals. So that's how we form the hybrid orbitals. And they're commonly used to explain bonding in compounds that have more than 2 elements in them, or more than 2 atoms. So it's a convenient way to explain bonding in this regard. Okay. So let's take a look at what these orbitals look like. Okay, so here's sp2, we have sp, sp3, sp3d, and sp3d2. Okay, so they look very similar to p orbitals, but as you go from sp to sp3d2, you see they kind of resemble more d orbitals now, or a hybrid of d and p orbitals. And the only one that looks kind of like a p orbital is like the sp, because it has the most p character, and it's somewhat more circular because it has s character as well. Okay. All right. So let's stop there, and we'll pick up this where we left off in the next lecture. So I'll see everyone in the next lecture. Okay? Take care.